Good morning, all. Today we discuss the application of operational amplifier, integrator, and differentiator. We know that using operational amplifier, we can manipulate mathematical operations. Here we discuss how the operational amplifier can be used as integrator and differentiator. A circuit that performs the mathematical integration of input signal is called an integrator. The output of an integrator is proportional to the area of input waveform over a period of time. It is the significance of integration. That is, the output of an integrator is proportional to the area of the input waveform over a period of time. The most popular application of an integrator is to produce a ramp output voltage. Ramp voltage means a linearly increasing or decreasing voltage. Now the figure shows the circuit of an op-amp integrator. When we looking at the circuit, it is clear that this circuit contain a feedback path. There is a feedback, that is, the output is feedback into the input, but instead of a resistor, here there is a capacitor. Okay, and so in the circuit it consists of an op-amp, an input resistor R, and a feedback capacitor C. And here the feedback component is a capacitor instead of a resistor in the previous cases. When the signal is applied to the input of the circuit, the output signal waveform will be the integration of input signal form. Or we can say that the output must be the integral of the input voltage. Now we go to prove it mathematically using this circuit. When looking at the connection diagram, we can say that due to the virtual ground and high input impedance of the op amp, the current flowing through the resistance R will flows through the capacitor because of there is no current flowing into the op amp. Okay, then the current I will be flows through the capacitor. So we can say that I must be equal to IC. The value of I must be equal to IC. Then we have to find the values of I and IC. We have to find the current through the resistor and the current through the capacitor. First, we have to find the current through the resistor. For that, we know that the voltage across R, voltage across the resistor R is equal to, that is equal to, here it is the resistor R, here the potential is Vi and here the potential is 0. Then Vi minus 0, that is equal to Vi. Okay. Then the current through R, current through the resistor R, let it be I, small I, that is equal to, current must be equal to voltage divided by resistance. Then I is equal to Vi divided by R. Next, we have to find the value of IC. For that, first we finding the voltage across the capacitor C. Let it be Vc. Vc is equal to what? Here it is 0 minus, at the next end the voltage is V0. So Vc is equal to minus V0. Then the current through the capacitor, that is represented by IC, that is equal to, IC is equal to minus V0. The current must be equal to find the current. Here this is capacitor, then we can express this current in terms of charge. IC must be equal to, I write it, it is dq divided by qc, dqc divided by dt, d by dt of charge. Okay, as in the case of capacitor, we use this expression. Okay, and we know that the expression for I write here, we know that the value of QC, Q is equal to C into the voltage across capacitor, it is CVC, and here VC is equal to minus V0, then QC is equal to minus C V0. So we write here, it is equal to d by dt of, we substitute for QC. QC is equal to minus C V0. Okay. Or that is equal to minus C is taken outside, minus C into dV0 divided by dt. And this current is equal to VI by R. So equating as I is equal to IC, we can write VI, I write in this way, IC is equal to IC, the value of IC is equal to minus C dV0 divided by dt, that is equal to VI divided by R. We have to find the value of V0. So we arrange this equation as dV0 divided by dt is equal to what? dV0 by dt is equal to minus of 1 by minus of 1 by RC into VI. And now we have to find the value of V0. dV0 by dt is equal to this quantity. To obtain V0, we have to integrate both sides. Then V0 must be equal to integral of minus 1 by C minus 1 by RC VI. Okay. For that, we take dt this side and we integrate dV0. Then V0 is equal to minus 1 by RC integral VI integral VI dt. Okay. So here we get the expression of output. It is the expression of output. From this, it is clear that the output is proportional to integral of input. Okay. And here there is a minus sign. Okay. The negative sign shows there is an inversion and there is a scale multiplier 1 by RC. Okay. We can only say that the output is proportional to integral of input. Okay. Is it clear? So this circuit working as an integrator. Now we go to discuss differentiator. A circuit that performs mathematical differentiation of input signal is called a differentiator. A circuit that performs the mathematical differentiation of input signal is called a differentiator. The output of a differentiator is proportional to the rate of change of its input signal. The output of the differentiator is proportional to the rate of change of its input signal. It is important application is to produce a rectangular output from a ramp input. When we give a ramp input, the output must be a rectangular wave. Now look at the figure. When we compare this connection diagram with the connection diagram of integrator, it is clear that the resistance and capacitance in both circuit is interchanged. Okay. We know that in the case of integrator, the capacitor is in the feedback and resistor in the input. And here the capacitor is in the input and resistor in the feedback. Now we go to analyze how the circuit is working as differentiator. We have to show it mathematically. Okay. And in this case also, we can say that due to the virtual ground and infinite impedance of op-amp, all the input current IC flows through the feedback resistor. Okay. So here IC must be equal to IR. And for that, first we have to find the voltage. First we have to find the voltage across capacitor. That is equal to Vi minus 0. That is equal to Vi. Okay. And to find the current IC. IC is equal to what? IC can be written as dQc divided by dt, and QC must be equal to QC is equal to what? QC is the charge stored in the capacitor, that must be equal to the capacitance into the voltage. Okay. And the voltage across the capacitor is Vi. So we write d by dt of C into Vi. Okay. It can be written as C into dVi divided by dt. And next, the voltage across R. Voltage across R is equal to 0 minus V0, that is equal to minus V0. And the current through R. Okay, let it be IR, or that is equal to minus V0 divided by R. And we know that IC is equal to, as IC is equal to IR, IC is equal to IR, we write C dVi divided by dt is equal to minus V0 divided by R, or V0 is equal to minus RC dVi divided by dt. It is the expression of output of differentiator. Then it is clear that output is proportional to the differential of input, but there is a inversion and a scale factor. So the equation shows that the output is the differentiation of the input with an inversion and a scale multiplier of RC. It is the proof of working of a differentiator. Now we conclude the session, and the topic of operational amplifier is completed. Okay, thank you.